Hello, my name is Michael Hotard and I'm a student in Math 23A. I'm going to try to walk through our proof 9.2, the infinite triangle inequality. We went over this in class. I had a little difficulty understanding why we were doing all the steps, so after talking through with some other students, I think I understand it better. And hopefully after this you can understand it a little better too. The first thing we're given is this equation here. And we want to show that this holds. We are told that we can assume that, actually this should be, we are told that this amount on the right is summable, but we don't know much about what's on the left over here. So that's kind of where we want to start. So first we want to show that this indeed is convergent, just to give us a sense of what's going on. And sorry, I'm going to correct some of the things while I do this. First, consider the jth component. So we know that the length of aij is less than or equal to the length of ai, and this holds for any type of vector. So, using the comparison test, we can see that the series of aij is convergent because we were told that this series was convergent. Next, we know that if we remove the absolute value signs, this is still convergent because of the absolute convergence theorem. Finally, we know that the series of I equals 1 of ai sum to infinity is convergent because we know that the component sequences are convergent, and if the component sequences of a vector are convergent, the vector is also convergent. Thus, we know that the absolute value of this is also convergent. So now we know something about the left-hand side of the equation, which is great. It's more than when we started. Now we're going to establish the triangle inequality for m vectors. Ultimately, we're going to try to get this m up to infinity, but we're not ready yet. The base case for this is m equal 2, and our hypothesis is that the summation of I equals 1 ai to m is less than or equal to the summation of I equals 1, the absolute value of ai to m. Paul didn't write these out, and I thought it was just helpful to kind of walk through really what induction we were doing here. So we can see that for the base case of m equals 2 is I equals 1 ai and a 2 here. This equals a1 plus a2. That's what this says. And this is less than or equal to a1 plus a2. The absolute value signs move to the outside by the triangle inequality, which we proved earlier in the year. So we know that this is true for a base case of 2. Is it true when it's no longer 2 but m? We have to use induction to show this. So we've established this for a base case of m. Let's see if it holds for m plus 1. We set up our induction by saying the sum of m plus 1 ai, I equals 1, equals, and now we're just breaking off the m plus 1, and over here is where we use our regular old triangle inequality. Here we have two sums inside an absolute value sign. So over here we're going to take the absolute values of the sums, and we know that's less than or equal to the original term. Now we're going to insert our hypothesis. And if you remember, our hypothesis was that we could say that this is less than or equal to this. So that's what we do. We insert our hypothesis, and then we bring back this m plus 1, and what do you know? Our original idea holds. We have shown that the summation of I equals 1 ai to m plus 1 with the absolute value on the outside is less than or equal to the summation of I equals 1 of the absolute value of ai m plus 1. This is great. Great progress for us. We're not quite to infinity yet, but now we have m. We know that the summation of I equals 1 ai to m is an increasing sequence of partial sums. This is an important fact. That tells us that this is indeed less than or equal to the summation of I equals 1 ai going to infinity. If you think about this, if this was not true, if this was possibly a decreasing sequence, then it could be that as we get to infinity, this actually decreases. But because there's absolute value sign, we know it's increasing, and we know that for m, as we go towards infinity, it's going to be less than or equal to. Because this is absolute value sign, there's no way that as we go to infinity, m is going to be less than that. I didn't quite understand that the first time through. We have established that the summation of I equals 1 ai to m is less than or equal to this. We did that up there in our triangle inequality. And by the transitive property, we know that this is less than this. This is also interesting to us because now we know that this is a convergent series in the closed set of 0 to this. And what we know is that the limit of a convergent series in the closed set is contained in the set. So we know that the limit for this must be less than or equal to the maximum in the set, the supremum here, its upper bound. So we know that the limit of this is the summation of I equals 1 ai to infinity. Thus we know that the limit is contained in this set, so we know that it's less than or equal to the upper bound of this set, and we know that this is less than this, and that's it. We established that the triangle inequality holds for an infinite series of vectors. However, note this does not hold for an infinite dimension vector space. That's important to note. I believe it has something to do with one of the first assumptions we had dealing with components and how convergent components implied the vectors were convergent. But just as important to note, this works for n-dimensional vector space but not infinite. Thank you.